Hello guys, this is CodeNCode and this is the second lecture of this basic algorithm series, and in this lecture we are going to see the main core of binary search and how the binary search is applicable, and after this lecture we'll be able to tell on which problems binary search is easy, on which problems we can apply binary search. So let's start the lecture. So there are certain terminologies that we will be using. The first one is active range. So active range is represented by two pointers L and R, which we use in binary search. So active range represents the range in which your answer may exist. So we will be representing that with L and R, of course. Now for this lecture series, I am assuming that you are aware of the basic implementation of binary search. The basic implementation in which we are given a sorted array and you are given an array, an element, and you have to tell whether that element exists in the array or not. So that is the most basic implementation of binary search. I'm not going into the detail of that, and I'm not going to explain that. There are a lot of resources you can study the most basic implementation of binary search, because in this lecture series we are going to look into more advanced aspects and the use cases of binary search. So this is the basic implementation, what it looks like. This is currently a current active range LNR. This is the array and this is the element you are going to search in the array. So while the range is valid, which means left comes before right, or low comes before high. If low crosses high, which means the range is invalid. In that case we will stop. Otherwise we will calculate mid and then check whether the mid element is equals to the element we are searching or not. We are assuming that the array is sorted in non-decreasing order. So if the mid element is equals to key, we would return this is mid, not midi. That is a typo, I guess. So if that happens, if mid element of array is equals to key, we would return the index, which is mid currently. Otherwise we would reduce our active range by half. If the current element is smaller than the element we are searching, and since the array is sorted in non-decreasing order, all the elements left to the mid will be smaller than key as well. In that case we will update the left pointer to be mid plus 1. Otherwise we would update, or we will discard the upper half values and set h is equals to mid minus 1. So this is how, or if after running whole loop we didn't find any element, which means the element doesn't exist in the array. That is why we would return finally -1, indicating we didn't find the element. So this is how most basic binary search technique works. But what makes binary search applicable to this array? The answer is the array is sorted. Yeah, that is very true. But what if we are here to apply binary search on a function like ax square plus bx plus c, and you have to tell the minimum x? You are given a, b and c, and the equation is and the function is fx is equals to ax square plus bx plus c, and then we are to find minimum x such that ax square plus bx plus c is greater than or equals to say 10 to the power 5. There is nothing to be sorted here. So what makes us be 100% sure that okay, we can apply binary search to this problem? Because here in the example that I just told you, here there is nothing to be sorted. There is no array, there are no integer elements, so there is nothing to be sorted there. What makes us 100% sure that okay, we can apply binary search there? Well, there is a very important property of a function which makes binary search applicable on that. And that property is not only the sorted array property. This is actually monotonicity. A function is called monotonic function if it doesn't change its behavior. That is, if suppose this sorted array, if I plot this sorted array on the graph where indices are plotted against indices are on x-axis and the values are on the y-axis. So at index 1 we are having value 1, as you can see. At index 4 we are having value 4, at index 5 we are having 6, so at index 5 we are having 6, and so on. The graph you'll see forms a non-decreasing graph, and this graph is monotonic. What monotonic means is that the graph will not change its behavior. That is, the function was non-decreasing and it will be non-decreasing throughout its domain. So you see, the function never decreases. It only the function when you move towards the right on the x-axis, the values either increase or remain the same. They do not decrease. That is why the function is called non-decreasing function. And since it doesn't change its behavior, there are functions which actually change the behavior, like the sine function or cos function, the trigonometric function. So the sine function is a trigonometric function which changes its behavior after every 2 pi interval. So that function is changing its behavior. That is why the function is not monotonic, but this function is. Now since this function is, after sorting the value, the function becomes the monotonic function, and that is why we are able to apply binary search on there. Now there are 4 different kinds of function. First is increasing or strictly increasing. In that case, what happens, if x1 is smaller than x2, then fx1 is smaller than fx2. That means if you are going towards the right, if you are moving towards the right on the x-axis, then the value of those points strictly increases. Every next element on the graph is strictly greater than the previous element. That is what makes it strictly increasing. Now there is strictly decreasing function. If x1 is smaller than x2, then fx1 is greater than fx2. That means every next element is strictly smaller than the previous value. That means it is strictly decreasing. Now then comes non-decreasing and non-increasing functions. Non-decreasing function does not decrease. That means the next value is having value either equal to the previous one or greater than that, but it doesn't decrease, right? Similarly for non-increasing function. So this function right here that you see, after sorting this array, you get this function, and this function is actually non-decreasing function because all of the values, every value you take on the ith point is either equal to the either equal to previous value or greater than that. For example, this point is greater than this one, but this point is equal to this one. So none of the value when you move from left to right is going to be smaller than the previous one. That is why this function is called non-decreasing, because it doesn't decrease. Once it reaches a certain point, like at this point we have reached value 7, at index 6 we have reached value 7. All of the points that are on the right side from index 6 will be either equal to 7 or more than that. They will never decrease. That is why the function is non-decreasing. Similarly, for the rest of their definition, the rest of functions behave. Now the behavior of all of these functions is monotonic. They do not change their behavior. That is why if we have any function encountered, we can 100% apply binary search there, because they follow monotonic property. Monotonic property gives you an assurance that helps you reduce your active range by half. So what we do here is, we suppose active range is this 1 to 9. There are 9 elements. You are searching for, say, element 9. So what you do, you calculate the mid element, which is 5. 1 plus 9 divided by 2 is 5. So at index 5 you see what value we have value 6, and you are searching for, say, 9. So if this is smaller than 9, of course all of the elements before it are smaller than 9 as well. So this gives us a prediction that helps us to reduce our active range by half. So what we can do, we know, okay, this element and all of the elements below it towards the left are smaller than the value that I am searching, so all of this range is actually useless to me. What I can do, I can update my left pointer, which was here, to mid plus 1, because all of these elements are useless. My result must be from mid plus 1 to higher. So the monotonic property gives you assurance. If the function was not monotonic, then we cannot apply this concept. Let me show you with an example. This, if you see, is not a monotonic function. So suppose your active range was such that, suppose you are searching for elements at 12, and you know 12, suppose we were searching for element 9. You can see 9 exists here at index 6, right? So your ln are such that you found the mid you calculate, your L and R, that is the left and the right pointer, are such that the index you found, the mid index you found is 7. You see, okay, 7 value, at index 7 I am having value 6, and since I am searching for value 9, and since this element is smaller, so all of the element below it will be useless. But that doesn't follow here, because this function is not monotonic. So before it may be the values which are greater than it, and also before it can be values which are smaller than this. Similarly, the same follows on the right hand side of this. So there is no prediction that enables us to reduce our active range by half. That is why non-monotonic functions which change their behavior are certainly not the one we can apply binary search on. Let me show you some of the examples which are obvious one, and one example which is non-obvious, as an example where we'll try to apply binary search. First problem I'll show you is from here. First problem is from Hacker Earth. This is Monk encounters with polynomial. So Monk have a polynomial ax square plus bx plus c. So you are given 4, there are t test cases. Test cases can be as large as 10 to the power 5, and each time you'll be given 4 integers a, b, c and k. A, b, c, you can see, are the coefficient of x square, x and constant term respectively, and then we have to find smallest x such that ax square plus bx plus c is greater than equals to k, which is the 4th integer in the input. So a, b, c and k are given. All a, b, c and k are strictly positive integers. Now we have to find smallest integer x such that is ax square plus bx plus c is greater than equals to k. Now this problem, this function that we have right here is actually monotonic function. The function is quadratic function, and since the input values are strictly positive, the input values a, b and c are greater than 0, or they are strictly positive. So we know quadratic function forms an upward or downward parabola, right, depending upon the coefficient of x square. If coefficient of x square is negative, then the parabola is downward, otherwise this is upward. You can try to plot the graph of any quadratic function and you can confirm it. Now since all of the values are, all of the coefficient of x square, x, all of these coefficient a, b and c are positive, hence this is an upward parabola. And since we are searching x in the range from 0 to only for positive values, we are searching x only for non-negative values. Sorry, we can have 0 as answer as well. So since we are searching values which are non-negative, that is, we are searching on the positive, on the right hand side of the graph, that is from x is from 0 to infinity. X can be anything from 0 to infinity, and in this domain the quadratic function is actually increasing. To prove this function is increasing, what you can do, of course this is the problem that find the smallest x, and that fx is greater than equals to k. To prove that this is an increasing function, fx should be smaller than fx plus 1, right? The next element must be greater than the previous element. This is the definition of a strictly increasing function. So you can put in the function x and fx plus 1 and you can evaluate it. If you put x, of course the equation on the left hand side would be ax square plus bx plus c. On the right hand side it would be ax square plus, since on the place of x you would put x plus 1 and there is a square, so this is what you would get. If you evaluate it, you'd see that after multiplying all of the terms and rearranging them, we get ax square, right hand side we get ax square plus bx plus c plus 2ax plus a plus b. Now since all of these terms are non-negative, hence this all of these terms are actually positive. So we can see this terms is these term add something extra to ax square plus bx plus c, which is on the left hand side. So the right hand side is strictly greater than the left hand side, which means fx plus 1 is strictly greater than fx, which means this function is actually not only monotonic but strictly increasing function on the positive side of x-axis, because that is the range that we have to search from 0 to we have to print the answer one of the positive integers. So our search area is only the positive side of x-axis, and and the quadratic function is actually an increasing function. So here the function is increasing function, which means it is monotonic, and hence we can apply binary search here. So in this problem you can actually apply binary search and solve this. There's same problem foo and exams, I guess, foo and exams, and there is a quadratic function, cubic function instead of a quadratic function. So you have to find smallest k such that you have to find smallest t such that f of t is smaller than equals to k, but f of t plus 1 is strictly greater than k. And now f of t is equals to at cube plus bt square plus ct plus d. So this is the function. Again, the value we are searching is on the positive side of x-axis, or t-axis in this case, because we are searching for t, and this function is actually increasing. You can prove it by yourself. Now there is one example, that is aggressive cows, where there is no function which is obvious that we have to prove that this is monotonic. For example, the problem is you are given n barns and c cows. So these are the position of barns and these are the cows. You have to place each cow in one of the barns such that the minimum difference between them is maximized. So these are the position of barns and we have to place 3 cows. So you see, one way is to place first cow in the first barn, second cow in the second barn, and third cow in the third barn. So the minimum distance would be 1, that is the distance between the first and the second cow. Other way is to put the cows in first, second and third barn. In that case the minimum distance would be 3, that is the distance again between the first and the second cow. And the third way is, there are more than 3 ways, I'm just showing the third way. You can place the cows in barns with position 2, 4 and 9. In that case the minimum distance is 2, because the minimum distance, the distance between the first and the second cow is 2, and the second and the third cow is 5. So the minimum is 2, of course, so the minimum distance comes out to be 2. Since we have to maximize the minimum distance, so we will go with the second way, and this is actually our answer. So the minimum distance we are able to achieve after the minimum distance we are able to maximize is 3. So the answer is 3. Now the question is, here is nothing, we can't see here a function, an obvious function which we need to prove monotonic. Like here in the first 2 problems we were having functions which we needed to prove monotonic, because those were the function which needed to be evaluated on the in the given problem. But here we see there is no obvious function here in the aggressive cows problem. So what we would do, we would define our own function which will help us to solve this problem. First important observation is that we need to maximize the minimum distance between them. So we'll define a function using this fact, the minimum distance, using minimum distance, because we'll apply binary search on minimum distance. So I define a function fx as the number of cows we can place such that the minimum distance is greater than equals to x. Again, fx is equals to fx is equals to number of cows I can place such that the minimum distance is greater than equals to x. This function I can use to calculate to apply binary search and calculate minimum distance. First, let's evaluate the function on certain values and let's prove that this function is actually monotonic. F of 1, that is, place the cows such that the minimum distance between them is greater than equals to 1. I can place 5 cows. I can place first cow on 1, second cow on 2, so the distance between them is of course 1. Third cow I can place on 4, the distance between these two would be 2. fourth I can place on 8. This distance between them is 4, which is of course greater than equals to 1. And the fifth cow I can place on 9. Again the distance between them is 1, which is greater than equals to 1. So I am able to place 5 cows. So f of 1 is equals to 5. Similarly, if you would evaluate f of 2, it would come out to be 3. Similarly, for f of 3, it is 3. Example, you can place first cow on 1, second cow on 4, and third cow on 8. So you will be able to place 3 cows. Similarly, these are example of rest of for certain values. Now, how to know that this function is actually monotonic? Well, if you see one of the properties, if you are able to place y cows such that the minimum distance between them, the distance between them is greater than equals to x, okay, then you will be able to place y or more cows such that the distance between them is greater than equals to x minus 1. This property, this function holds, and hence this is a non-increasing function, which is one of the monotonic function, and hence I can apply binary search here. Now, how I am so sure that okay, if I am able to place y, this is literally the common sense, but still, if you are able to place y cows such that the minimum distance between them is greater than equals to x, right? So what makes us so sure that okay, we'll be able to place at least y cows? F of x minus 1 is greater than equals to y, which means its value f of x minus 1 is at least y. This is what it means. So I'll be able to place y cows, at least y cows, such that it's where the minimum distance or the distance between them is greater than equals to x minus 1. How that's possible, and how to assure that? Well, whatever configuration you are having for f of x, the same configuration you can show for f of x minus 1. And because f of x means the cows are placed such that the distance is greater than equals to x, will be valid for f of x minus 1 as well. This way we can see that f of x is actually a monotonic function, which is non-increasing function, and hence we'll be able to apply binary search here. So you see, this problem doesn't have a function, doesn't have an obvious function which needed to be proved to be monotonic function, right? So we define our own function which will help us to solve this problem. And how this will help, I'll be telling you in the lecture. I'll be teaching you how this function is useful to apply binary search and solve the problem in the lecture where we will be solving aggressive cows problem. So this lecture is already too long, I guess, so I'll be stopping here, and from next lecture onwards we'll be taking certain problems on binary search and we'll be solving one by one one of the most important and the interesting problems. So this was all for this lecture. Thank you guys for watching, and if you have any doubts and query, you can of course ask in the comment section. Thank you, and keep coding.